All right, so thank you. As Yaoyun mentioned, the title of this project is Interactive Proofs with Approximately Commuting Provers. And this is work with Thomas, who's here. All right, and so let me just get straight to the point. This is sort of a new title. I don't think this phrase has ever appeared in the context of quantum information or anywhere else. So let me sort of address what does this actually mean? Or at least by the end of my talk, hopefully it will be clear what this actually means. For now, I'm just going to jump to what is basically the main motivating question behind this work, which is this one. How can you compute the winning probability of an arbitrary non-local entangled game? And so I guess this question is probably hopefully much more recognizable to people in this audience. And so this is the sort of quantity that you would like to compute, where this maximum is taken over all possible POVM measurements, and also over all possible shared entangled states. And so this drawing is just meant to represent a standard game. So the referee passes classical bit string messages to two players, or I'm going to call them provers, or in device independence, they're often considered to be black boxes that you're testing. And these provers return to you classical bit string messages. And there's a predicate that the referee applies, which determines whether or not the provers win, based on the inputs and the outputs. So this is the setting that we're considering, and so I guess this is we just had this great survey talk about sort of specific cases of games where you have very strong results. You have sort of self-testing results and rigidity results. This is going to be sort of asking a much weaker question, but about the class of all games. So this question is just, how can you compute the winning probability? All right, and actually this question itself is a bit presumptuous. The real question you should be asking is, can you compute the winning probability? And the reason you should ask that question is because it's actually not known. The problem of computing this quantity is not known to be computable. Or if you phrase it as a decision problem, it's not known to be decidable. OK.
But it's not known to be uncomputable either.
That's correct. And as you'll see, it's sort of one of the most interesting things about this question is that I think there's a strong intuition that comes from studying quantum information that tells you how you might want to try to compute this. And the real barrier here is that we don't know how to prove that it's correct. And so that's sort of the focus of this work. Although we won't actually resolve this question, but I think hopefully we'll have something interesting to say about it. OK. So this is yet another way to phrase the fact that we don't know this problem is computable. And the reason, sort of the fundamental problem that keeps us from at least supplying some kind of brute force algorithm for this problem is that we don't know, we're sort of maximizing over these POVM measurements and over this state, but we don't know how large a dimension we need to get close to the optimal winning probability. And there are really no bounds for arbitrary games. So that's the state of understanding, at least sort of rigorously proved results. But there are special cases that we do understand. And these are the things that people studying device independence are probably very familiar with. So unique games is one case. They're Kochen-Specker type games and XOR games. And in the context, in the context of this talk, probably the most relevant thing is XOR games. This may also be what's most familiar to everyone here. And the reason that those are the most relevant is because there's a well-known SDP algorithm for computing the winning probability. And actually, in this talk, I'm going to just write up the SDP constraints. It's the best method I found for conveying it. But if anyone has questions about them, please let me know. So this is the SDP for XOR games. So now instead of maximizing over POVM strategies, you're actually maximizing over unit vectors. But other than that, it's this inner product of unit vectors. But other than that, it's sort of the same maximization. But that's quite nice because without loss of generality, you can assume that you can place all these unit vectors in bounded dimension. There are only so many inner products here. You can place all this in a vector space which has dimension, which is sort of polynomial in the number of inputs and outputs. And the reason that we know that this statement is true, that the optimal entangled winning probability of this game, or of any XOR game, so in order for this to be true, the predicate has to be an XOR type predicate. So the winning condition has to depend only on the XOR of the two outputs, A and B. They have to be single bits. So the reason we know this is true is a theorem of Searleson. It's one of the sort of foundational works in quantum games. And there's a similar result for unique games. It uses essentially the same SDP and a completely different analysis, but you can compute, where you can decide a certain problem for unique games as well. Okay, and the question we're considering is, what about general games? And we'll sort of pursue a strategy that's been proposed by others, but that's kind of built in analogy to the SDP that's used for XOR games. But that SDP itself doesn't work for general games. Yeah. Yes, sorry, that's a good point. So I'm going to, all of my notation and diagrams will be for two-player games. There are results here which easily extend to multiplayer games. Okay. Right, and please feel free to ask if anything else is confusing. Okay. And again, so as soon as this single round SDP fails, we just arrive back at the original question, or the same lack of understanding that we had at the beginning. We don't know how to bound the necessary dimension. But there are two proposals for getting around this. And those two are this paper of Navasquez, Pronio, and Aiken, and there's also another paper, Doherty, Leong, Toner, Werner, and they both propose an SDP hierarchy. So they propose some kind of huge generalization of the SDP that's used for XOR games. And the two approaches actually turn out to be dual to each other. So from now on, I'm going to package them as two sides of the same SDP hierarchy. I'm just going to coin this as the QC, the quantum correlations SDP hierarchy. And so let me try to explain this hierarchy a little bit. Actually, I'll put up the actual definition for you in a second. But the intuition behind it is that if you recall the SDP for XOR games, it had a vector corresponding to every POVM measurement. And the idea was that these, like the vector V sub P, would represent P, that measurement, acting on the shared entangled state. So that's like the intuition. Now, to make that rigorous, you needed the rounding that's given by Searleson's theorem. So these proposals extend that intuition by, instead of having a vector for every POVM measurement, they consider vectors for every string of POVM measurements of length n. So that's the nth level of the hierarchy. Or in other words, you can define an alphabet which contains all the POVM elements as formal symbols, and you can look at all words of a certain length on those formal symbols, and you can phrase all of this as you can phrase your entire optimization problem as an optimization over the space of positive semi-definite matrices. So this is gamma. So a gamma is it's a huge matrix. It's indexed by S and T, which are words. They're formal words in the operators P and Q. OK, so there's a lot of notation here. I'll just try to move slowly through it. The reason that this is equivalent to considering optimizing over inner products is because of this Cholesky decomposition, which allows you to, it means that a gamma, which is positive semi-definite, can always be expressed in this way. So each element in gamma is actually equal to inner product of some vectors. So optimizing over these positive semi-definite matrices is the same as optimizing over a huge set of inner products. All right. So here, I've actually put up the entire SDP hierarchy just for good measure. This is the hierarchy that they propose. And I guess it's probably a bit dizzying to see it all at once. But if you can only sort of consider two constraints, these two equations are the ones to sort of consider. So these are basically, there's a gamma's huge positive semi-definite matrix. And we're trying to enforce that if you're looking at any inner product of a huge string of operators, so the shared state dotted around a large formal, a large product of sort of formal symbols, that it should be the case that you can swap any P and Q, meaning that we're trying to enforce the fact that operators P and Q should commute with each other. They actually should be in tensor product with each other. Like P are the measurements that one player is making, that Alice is making, and Q are the measurements that Bob is making. So they should be in tensor product, which means that they commute. So this is just trying to enforce the fact that all of these measurements commute. And there were some results in the original papers on this, which sort of bring out this commutation aspect. But they work under specific assumptions. So it was demonstrated in these papers that, first of all, sort of if we define this omega n to be the value computed by this nth level SDP hierarchy, then this is, by definition, essentially an upper bound on the quantum winning probability of a game. And furthermore, it's a decreasing upper bound. So you could hope that it actually converges to the value. And that's the idea. And in this Navascus, Peronio, and Aiken paper, they actually prove that this does converge, but under an assumption called the rank loop condition. They have to assume some special property of the optimizing PSD matrix. But this is not known to be true in general. There are many different gammas that could achieve this optimum. They may not all have the rank loop condition. And sort of attempting to restrict your optimization problem to just gammas which have this condition can increase its complexity enormously. And probably most importantly, there's no guarantee that there will, for a given game, that there will ever be a gamma satisfying the rank loop condition. So this is a nice technique, but it won't completely resolve this general games case. And in fact, it's far from it. But it does give us some good intuition. And it demonstrates something about how important commutation is to this discussion of optimizing over tensor product strategies. All right. So let me describe what they did in the Navascus, Peronio, and Aiken paper a little bit more carefully. So if you recall this Cholesky decomposition, so each element of these large PSD matrix can be considered as an inner product, and we can actually just imagine that we have access to those vectors, then we can actually define projectors in this space that was created by SDP optimization. So we can project onto the span of all vectors that look like this. So strings of the vectors indexed by strings of formal symbols ending in a P or ending in a Q. And these vectors are supposed to represent the measurements, the strategy that's constructed by this SDP hierarchy. And the NPA paper, what they showed is that as long as the rank condition holds, these measurements actually commute with each other. So all the Alice measurements and all the Bob measurements commute. And furthermore, there's a result in representation theory that allows you to conclude that as long as you have commuting measurements in finite dimension, you can basically find a transformation that puts them into tensor product form. So you can actually, optimizing over perfectly commuting measurements is like the same as optimizing over tensor product measurements, which was our original goal. Sort of this quantity, the maximum over all possible tensor product POVMs was maximizing that was our original goal. Okay, but all of this is only true if the rank loop condition holds. What if it doesn't? Well, the lesson we learned from the representation theory result is that commutation is important here. Maybe you can rephrase all of these results as instead of trying to produce tensor product strategies by rounding your SDP, you just try to produce nearly commuting strategies. And that's the idea behind this work. And sort of the main result of this work essentially says that is the case. So you can, if you have a solution to the nth level of this SDP hierarchy, you can round it to actual quantum measurements that are not in tensor product, but they're very close to commuting. So you can actually construct measurements for Alice and measurements for Bob, and while they're not physically separated in the model of quantum information, being in tensor product, they're very close to commuting. If they commuted exactly, then by the representation theory theorem that I mentioned earlier, they actually would be in tensor product. And so let me describe, we construct these measurements using a rounding scheme. And let me now describe our rounding scheme very briefly. So I go back to the Cholesky decomposition again so I can describe these vectors indexed by formal symbols. And now we actually define a projector onto vectors indexed by formal words which are less than some specific length, j. And our rounding procedure is then this. So we sort of weight we take the projectors that were produced by the NPA paper, and we truncate them more and more severely as the length of the words gets longer. So now I'm just restating the main result, but with explicitly writing out this rounding procedure. And in particular, we sort of achieve bounds on the operator norm of the commutator of these measurements. So let me try to explain briefly the intuition behind this result. The idea is this. The original measurements produced by the NPA sort of rounding procedure had a special structure. If you put them in the correct basis, and the correct basis is the one where you first start with all vectors of, this is the sort of vector corresponding to the empty symbol. Then vectors indexed by single POVMs, just like in the first level of the SDP hierarchy. Then all vectors indexed by length 2 words, and so on. Then you get a structure where the only non-zero elements occur in the red here. And you can take advantage of that structure. That's what our rounding procedure does by weighting sort of more and more severely the non-zero components that occur further and further down. And the reason that you could hope that this might work is that it already follows from the NPA result that if you restricted yourself to any fixed subspace, you would have perfect commutation within that subspace. And the only problem with that is at the very end, when you get to the nth level, it could fail very badly. So this kind of, in some sense, spreads out that bad failure at the nth level over many different levels. And that allows you to avoid this problem to some extent. So the natural question here is, if you have these close to commuting measurements, why can't you just prove or find measurements that are close to being in tensor product, or nearby measurements which are in tensor product? And that's what you could do in the exact case. When you had exactly commuting measurements, you could find, well, you could just show that those measurements were exactly in tensor product. And we're unable to do this, but largely because there are several barriers. One is that the natural conjectures you might make, which is that two matrices which are close to commuting are close to matrices which are exactly commuting or are in tensor product, is actually false in a sense. So there's an example by Wojciechowski. This is actually a whole industry in mathematics studying these type of examples. And another one is that other conjectures you could make which sort of avoid the problem here are closely tied to major open problems in mathematics. So this is a conjecture which would do what we want. It exists in a math paper by Ozawa, but it implies Cohn's embedding conjecture, which is a major open problem. So it could be very difficult to prove. So these are the sort of constraints that we're operating under. It's also part of what makes the problem interesting. We do have some partial progress. You can do the rounding that I mentioned to actual tensor product strategies in certain special cases. In the case where the games have only 2 inputs and 2 outputs for one player and k inputs and 2 outputs for another player, then you can do it. There are also some bounds showing that this rounding strategy is nearly optimal. And I'm running low on time, so I won't describe those. So the last question is sort of, if we can't solve Cohn's embedding conjecture, so we can't relate this directly to optimizing over true quantum strategies, what can we do to show that this is a useful rounding scheme? And the answer to that lies in complexity. So in this paper, we actually introduce a complexity class. And this complexity class is a relaxation of the class MIP star, which studies interactive proofs between entangled provers. And actually the one-round version of that, which is more or less just a complexity theoretic version of for studying the problem of optimizing quantum winning probabilities. And we relax this so that the soundness part only requires delta commuting strategies. Actually, I haven't defined that, but strategies in which the POVMs are delta away from commuting, or bounded, their commutators are bounded by delta and the operator norm. Right. I'll skip that motivation. And the reason that introducing this class helps us to motivate the problem is that now we can actually prove upper bounds on this complexity class, which just corresponds to the result that I mentioned before. So so you can sort of optimize over these single round, approximately commuting MIP star problems. But sort of more interestingly, or the sort of better motivation for why you would introduce this class is that you can also prove lower bounds. So and the paper shows that inexp is actually contained in this MIP, approximately commuting MIP star, although with sort of exponentially bad soundness. And the reason that this is interesting is it means that although we can't show that this problem solves the optimization over quantum winning or quantum strategies perfectly, it does mean that it's doing something non-trivial. So it can't be that this entire rounding scheme actually does nothing, because it contains this rather large complexity class. And this was proven actually using sort of a direct analog of this result of Ito, Kobayashi, and Matsumoto. And I won't go into that. I think I'll just end there.
Okay, thank you. Any questions for Matthew?
Yes.
One of your results, the one I'm trying to understand. So, it's correct that if I find a solution to a problem in the MPA hierarchy, let's say third level,
Yes.
then this means there is a quantum solution always such that the commutator between, so of course if I impose moreover that the commutator must be zero, then I may not find a quantum solution for that. If you say that
right.
I can allow commutators, operators that commute almost, then I can always find a quantum solution.
Yeah, so the almost, so the piece that we're missing is that almost commutation does not let us conclude that you're close to strategies that truly commute and would therefore be physically separated. So that's sort of the missing piece. But aside from that, let me go back. There. So you said the third level, the level of the hierarchy actually appears here in our bound. So the error, or the size of the commutators would be only constrained by how many levels you actually use. So this would probably have to go much higher than 3 in order to get a very small bound. But yes, other than that, that's right.
So you actually have the Pacquiao
Yes.
program for the binary
Right. Yeah, so that, did I skip it? Well, oh, here we go. Yeah, so right. So it makes sense that it's possible to handle this case because there's a result of Massanes that lets you compute the winning probabilities for games with 2 inputs and 2 outputs for every player. It uses Jordan's lemma. And this is based on a very similar idea. Although it's different to do the rounding in this setting. Like it's not a trivial direct implication of the Massanes result, but the Massanes result will handle the same type of games. Yeah, I don't know if that.
Questions? I have a question.
Yeah.
So suppose I know for a game, it's some finite level of the SDP hierarchy. Score. Does that imply that there is a optimal strategy?
Yes. So right. Right. Yeah. Actually, there's a second part to the rank loop condition that I mentioned. Yes. The answer is yes.
Under the
And
rank loop
yeah. So the
of that assumption.
Yes, let's see. You said it reaches the optimum value at a finite level.
Right, but that doesn't mean that these operators are finite
No.
in general. So the SDP, the variables of SDP are coefficients for multiplying Benjamin operator.
It is a finite size SDP. I believe you can just use the...
So the SDP, the entries of SDP
These.
variable are coefficients for the strategy, right?
You recover, like I was explaining, you recover the vectors from the Cholesky decomposition. There's a finite number of vectors, they are in finite dimensions. The strategy is defined as operators acting in that space. The space spanned by the vectors that you recover.
Yeah. Yeah.
Not necessarily of the solution that we find, but there will exist such a solution, so there will definitely exist a finite dimension.
So I have some